Hello everyone. So last time we looked at how to solve ODEs using power series method. So last time, power series method. And we saw the definition of power series. A power series is a series of the form, let's say A0 plus A1 times x minus A2 times x minus A squared, which is same as sigma an x minus a to power n, and from 0 to infinity. So this is a power series in general. Now Taylor series is a special case of power series. And we saw that Taylor series can be written as, let's say, f of a plus f prime of a times x minus a plus f double prime of a over 2 factorial x minus a squared, and so on. So we have the notion of power series and Taylor series. And we saw the definition of analytic function. So for analytic functions, f of x equals Taylor series expansion around x equals a for x close to a. And this is true for every a. And with some most functions that we are familiar with them are analytic, meaning that they are equal to the Taylor series, their Taylor series expansion. For example, e to the x can be written as 1 plus x squared over 2 factorial, and so on. We also saw the Taylor series expansion of sine x, cos x, 1 over 1 minus x. And we also defined radius of convergence. Now today we want to see how to solve ODEs. So solving ODEs using power series. So first we need some properties of sigma. But we can write each power series in the sigma notation. As you can see, we can expand it this way, or we can write it using sigma notation this way. Now, if you want to solve an ODE, it's easier to write it in the sigma notation and use the properties of sigma. So let's look at some properties. So basic properties of sigma. The first property is sigma, let's say CAN is equal to C sigma AN, and from 0 to infinity, and C is a constant here. So if you multiply your terms with a constant, you can always take the constant out of the sigma. Now the second property, let's say sigma AN, and from 0 to infinity, plus sigma BN, and from 0 to infinity. This can be written as sigma AN plus BN, and from 0 to infinity. So the sum of two sigmas can be written this way. Sigma AN plus sigma BN can be written as sigma AN plus BN. But we don't have this property for products. So for example, sigma AN times sigma BN cannot be written as sigma AN BN. So this is valid only if you have an addition here. And of course, subtraction is okay as well, because for subtraction, we know that if there is subtraction, we can take the subtraction inside. So if you have sigma AN minus sigma BN, if I combine first property and second property above, I can write it as sigma an n from 0 to infinity plus sigma minus bn n from 0 to infinity. And then I can write this one as sigma an minus bn n from 0 to infinity. So first I can apply property 1 to write this sigma in this form. And then I can apply property 2, and I write it as sigma an plus minus bn, which is an minus bn. So this is a property, another property of sigma. Now another property, if we change n to, let's say, n plus a, the starting index shifts a units to the left. This is similar to graph transformations. In graph transformation, if you change x to x plus a, like if you look at f of x plus a, the graph of this one has a units shift to the left. Similarly, if you change n to n plus a, the starting index shifts a units to the left. So sigma, if I have, let's say, sigma an x to the power n, let's say, or let me just sigma an in general, sigma an, and from, let's say, a to infinity, I can write this one as sigma a n plus a. So see, I'm changing n to n plus a. If I change n to n plus a, the starting index shifts a units to the left. So instead of a to infinity, I will have 0 to infinity. So this a, of course, doesn't have to be same as this a. It's not same as this a. I can use a different letter just to avoid confusion. So say, for example, n plus l, I can say l here. So we change n to n plus l, and starting index shifts l units to the left. Now the fifth property, sigma. Okay, fifth property about, let's say, differentiation. If you want to differentiate or integrate a series or a power series. So differentiating and integrating a power series. How can I do this? So let's say if I have sigma an x to the power n from 0 to infinity, and I want to differentiate it, I can write it as sigma n x to the power n minus 1, and then n from 1 to infinity. Doesn't matter, even if I say 0, then 0 times anything is 0. So I can start the index from 1 to infinity, because derivative of x to the power n from math 113, we know is n x to the power n minus 1, and an is a constant. So I can write it as sigma n x to the power n minus 1. And now if I, let's say, change n to n plus 1, if I want this power to be n instead of n minus 1, if I want it to be n, then I have to change n to n plus 1. So if I change n to n plus 1 here, I will have sigma n plus 1, a n plus 1, x to power n. And instead of 1 to infinity, we said if you change n to n plus L units shift to the left. So this will be 1 unit shift to the left. So then I'll have n from 0 to infinity. So similarly, we can write a formula for integration. This will be sigma an x to power n plus 1 over n plus 1, and from 0 to infinity. And if I change n to n minus 1 here, let's say again, if I want to make this power to be n, then I need to change n to n minus 1. And what happens if I change n to n minus 1? I will have to shift 1 unit to the right this time, because we just saw that changing n to n plus L shifts L unit to the left, the starting point. Now this one is n to n minus 1, so starting point will shift to the right 1 unit. So instead of 0 to infinity, I'm going to have 1 to infinity, and then I've changed I've changed n to n minus 1, so this will be a n minus 1 x to power n over n. Change n to n minus 1, and then here if I change n to n minus 1, I'll have n minus 1 plus 1, which is n, and here I'll have n minus 1 plus 1, which is n. So this is how you integrate a power series. All right, now let's apply these properties in order to solve a simple ODE problem. So example, use the properties above to verify that y equals e to the x is a solution for y prime equals y. So y prime equals y is a differential equation. And we know that e to the x is a solution for this. Now I want to use the power series method to verify that e to the x is a solution for this. So how can I verify that e to the x is a solution for this? Well, I have to differentiate this, but we want to use the power series. So first I need to write e to the x as a power series, because that's what the purpose of this question is, to use the power series. So first I need to write e to the x as a power series. So first, write y equals e to the x as a power series. Then I'll have e to the x equals 1 plus x squared over 2 factorial, x cubed over 3 factorial, which can be also written as sigma x to power n over n factorial, n from 0 to infinity. Now, this is my y, so I need to differentiate this. I want to verify y prime equals y. So I need to find y prime, which means I need to differentiate this and then verify that it's going to be same as y itself. So thus y prime will be derivative of this function And what is derivative of this function? It's going to be sigma n x to the power n minus 1 over n factorial, and from 1 to infinity. So you use property 5 here. I need to differentiate x to the power n, which is n x to the power n minus 1, and then start the index from 1 instead of 0. So that's what I did here. I differentiated x to the power n as n x to the power n minus 1, and then I started the index from 1. And then 1 over n factorial is a constant not depending on x, so I just transferred it. Now I can simplify this because n factorial can be written as n times n minus 1 factorial. So if I write it this way, then n cancels with n. Then I'll have sigma x to the power n minus 1 divided by n minus 1 factorial, and from 1 to infinity. And now I can change, because I want this power to be n in order to be able to compare with original y. In the original y, the power of x was n. So how can I do that? I can change n to n plus 1. So let's do that. Let's change n to n plus 1. And then I'll have sigma x to the power n over n factorial, n from 0 to infinity. You just saw that if you change n to n plus 1, the starting index shifts 1 unit to the left. So instead of 1 to infinity, I will have 0 to infinity. And this is exactly the expansion of e to the x, which was y itself. So we started with y prime. After some simplification, we saw that y prime is also e to the x, which was y. So that means e to the x is a solution for this differential equation. So y equals e to the x is a solution for y prime equals y. All right. Now, let's see how, so this one, the solution was given, and we just verified that this is the solution for this equation. Now, let's see whether we can find the solution. So let's say if we don't know that this is already a solution, how can we derive this solution? So to derive the solution for a given ODE using power series method, so first of all, the ODE that we are going to consider in this case will be an ODE of the form. So let's say consider, let's say second order ODE. Let's say P of x y double prime plus Q of x y prime plus R of x y equals 0. So let's assume we have an ODE of this form. So it's a second order linear ODE. And here P of x, Q of x, and R of x are polynomials, where P of x, Q of x, R of x are polynomials. And we want to find a solution for y. The goal, find a solution y that is defined for x close to some number, let's say x naught. So x naught is a fixed number in the domain of P of x. Here we assume that x equals x naught is in domain of P, and P is a polynomial, so domain of it is all real numbers. And we assume that this x equals x naught is not a root of P of x. We assume that x equals x naught is not a root for P of x, meaning that P of x naught is not equal to 0. So this is what we assume, that x equals x naught is not a root for P of x. You may wonder why. Well, the calculation turns out to be more complicated if x naught is a root for P of x. So if x naught is not a root for P of x, it's called an ordinary point for our ODE, and the calculation will be easier. If x equals x naught is a root for P of x, then it will be not an ordinary point and called singular point, and the calculation will be more complicated. So let me say, let's see definition below. The definition consider P of x times y double prime plus q of x times y prime plus r of x times y equals 0 if P of x naught is not equal to 0, then x equals x naught is called an ordinary point of this ODE, and if P of x naught equals 0, then x equals x naught is called a singular point for this ODE. So the our goal is to find a solution for P of x times y double prime plus q of x times y prime plus r of x times y equals 0 around x equals x naught using our series method where x equals x naught is an ordinary point. Ordinary point of this ODE. So this is our goal. We have an ODE, and P of x, Q of x, R of x are polynomials. We have a fixed point x naught, which we assume is not a root of P of x. Why do we assume it's not a root of P of x? Because if it is a root of P of x, then the calculation will be more complicated. So for now, we assume that it's not a root of P of x, and we want to consider a power series function, which is a solution for this, and the power series is supposed to be defined around, at least around x equals x naught. Around x equals x naught means to the left and to the right side of that point. Or more technically, on an open interval containing that point. So to do so, now what will be the procedure to find a solution? To do so, consider y equals, let's say, sigma. Let's consider a power series of the form, let's say, sigma an x minus x naught to power n, and from 0 to infinity. Then substitute back into the ODE above. In order to find a recursive relation for an. Recursive relation for an means like a relation of the form, let's say an plus 1 equals like something times an plus, let's say, something times an minus 1, or an plus 2 equals, let's say, something times an plus 1 plus something times an. So when we say a recursive relation for an, we mean a relation where an is given in terms of, each an is given in terms of the previous terms. So for example, an plus 1 is given in terms of an and an minus 1. Or an plus 2 is given in terms of an and an plus 1. This is called a recursive relation for an. So if I substitute back this equation into the original ODE, then I'll be able to find a recursive relation for an, and then I can use that recursive relation to solve my ODE. So use the recursive relation to find, let's say, A3, A4, A5, all these terms in terms of, let's say, A2, A3, A4, A5, and all these terms in terms of A0, A1. So A0, A1 are two constants, because remember, if you have a second order ODE, this is a second order ODE. The general solution will include two constants, two arbitrary constants, which can be found once the initial conditions are given. But if the initial conditions are not given, then the general solution will include two constants. Those two constants here are called A0 and A1. So you're allowed to have two arbitrary constants, A0 and A1, which are the constants included or involved in your general solution expression. And then you can find the rest of the terms like A2, A3, A4, and so on in terms of A0 and A1. To find this in terms of A0 and A1, and then the general solution, and then construct or form the general solution y equals sigma an x minus x naught to power n, and from 0 to infinity in terms of arbitrary constants A0 and A1. So this is how we can solve a second order ODE, and our solution will include two constants, arbitrary constants A0 and A1. Now, we can do a similar process for the first order ODE or for third order ODE. So I just explained it specifically for second order, but we can do a similar process for first order or third order and so on. So let me give you as a remark that a first order ODE of the form P of x times y prime plus Q of x times y equals 0 can be solved using a power series method. This is y equals sigma an x minus x0 to power n from 0 to infinity. Again, if x equals x naught is an ordinary point of the ODE above, meaning that P of x naught must be non-zero. So if P of x naught is not zero, again, we can consider a solution of this form, and then again form a recursive relation for an, then substitute back, find a recursive relation for an, and use it to find, let's say, A1, A2, A3, all these terms in terms of the arbitrary constant A0 the arbitrary constant A0, then write the general solution y equals sigma an x minus x0 to power n from 0 to infinity in terms of A0. So the only difference is that this time, because the first order ODE, the general solution will include one arbitrary constant, which we call it A0, and then we can find everything else, all the remaining coefficients in terms of A0. Therefore, we'll be able to write the general solution in terms of A0 only. So this is a recipe how you solve a first order ODE around a point x equals x naught, which is an ordinary point of this ODE, meaning that P of x naught is non-zero. And a similar process for second order ODE. The only difference is that for second order ODE, it will include two arbitrary constants, A0 and A1. And you can write the general solution in terms of A0 and A1 by finding all the remaining coefficients like A2, A3, A4, and so on in terms of A0 and A1. So let's look at some examples. Let's start with a very simple example. First order ODE that we considered above. So find the general solution solution of y prime equals y using power series method. So in above, we saw how to solve this ODE. We saw how to verify that y cos e to the x is a solution for this ODE. But now let's assume we don't know that that is a solution for this ODE, and we want to derive the solution using the power series method. So here x naught is not given. So let's fix it. We have to fix x naught. So we can fix it to be any arbitrary point, any ordinary point. Ordinary point here is what? So here p of x is 1. So that means any x naught is an ordinary point for this ODE. The coefficient of y prime here is 1. And the constant function 1 has no roots. So that means whatever I consider as x naught is not going to be a root for p of x. And therefore, whatever I consider as x naught is going to be an ordinary point for my ODE. So the easiest choice would be like x naught equals 0. If x naught is not given and I'm allowed to choose anything as x naught. So let's pick x naught to be 0. So let's pick x naught equals 0. Then what will be the power series function? So power series will be y equals sigma an x minus x0 to power n from 0 to infinity. But x0 here is 0, so I can write it as sigma an x to power n from 0 to infinity. So what will be y prime? Because I need to, once I write y in this form, then I need to substitute back into my ODE. Now my ODE is y prime equals y. So this is y, and so what will be y prime? Y prime will be derivative of this function, which will be sigma n an x to the power n minus 1, and from 1 to infinity. If I change n to n plus 1, we saw that the starting point shifts 1 unit to the left. So it's going to be sigma n from 0 to infinity, n plus 1, n plus 1, x to the power n. Now here, we know y prime must be equal to y. So that is the original ODE. And this is y prime, this is y. So let's equate them. What do I get? Sigma n plus 1, n plus 1, x to the power n equals sigma an x to the power n. And from 0 to infinity, and from 0 to infinity. So then I'll have, if I compare the coefficients, the coefficient of x to the power n, because these two functions are supposed to be identically equal to each other for every x. So that's what happen if every coefficient the left-hand side is equal to the corresponding coefficient the right-hand side. Now coefficient of x to the power n in the left-hand side is this guy here. So coefficient of right-hand side is of x to the power n is an. So this coefficient must be equal to an. So that means n plus 1. An plus 1 must be same as an for n bigger than equal to 1. So let's use this to find an in terms of a0. Remember, if you have a first order ODE, we can find all the coefficients in terms of a0. A0 will be our arbitrary constant. So let a0 be an arbitrary constant. Then what will be a1? A1 will be a0 over 1. And what about a2? So 2a2, if I replace n with 1. So this is for n equals 0. If I replace n with 1, then I'll get 2a2 equals a1, which is same as a0. So a2 will be a0 over 2. Now if I replace n with 2, I'll have 3a2 equals a2. So 3a3 equals a2 if I replace 3a3 equals a2. If I replace n with 2 here, in this equation, replace n with 2. So 3a3 will be a2, but a2 was a0 over 2. So a3 will be a0 over 2 divided by 3. And that's going to be a0 over 6, or 3 factorial. And then if I replace n with 3, again I'll get 4a4 equals a3. a3 was a0 over 3 factorial. So a4 will be a0 over 4 times 3 factorial, which is a0 over 4 factorial. So continuing this process, what do I observe? I'll observe that, let's say a5 equals a0 over 5 times 4 factorial equals a0 over 5 factorial. A6 equals a0 over 6 times 5 factorial, a0 over 6 factorial, and so on. An will be a0 over n times n minus 1 factorial equals a0 over n factorial. So if I substitute back, then what do I get? I'll get y equals sigma an x to the power n. And from 0 to infinity, we just verified that an is a0 over n factorial. So I can write the sigma a0 over n factorial times x to the power n. And from 0 to infinity, a0 can be factored out. So I can write this one as a0 times sigma x to the power n over n factorial. And from 0 to infinity. And this one is the Taylor expansion of e to the x. Taylor series expansion of e to the x. So I can write this one as a0 times e to the x. So this is the general solution. Of y prime equals y. And here a0 is an arbitrary constant. A0 is an arbitrary constant, and this is the general solution. A0 times e to the x. And this is the result that we have seen before as well, that the general solution of y prime equals y. Previously we said is y equals c times e to the x for arbitrary constant c. So here instead we said a0 times e to the x for an arbitrary constant a0. Okay, guys, so this is how we solve a first order ODE. We can apply a similar procedure, writing as a power function, power series function, then substitute back, find a recursive relation for an, and find all an's in terms of a0 in the case of first order ODE, and in terms of a0 and a1 in the case of second order ODE. And then we will have our general solution.